This is Albert Einstein, and this is how he changed the world with one equation. It looks scary, but it isn't just numbers and squiggles. This equation turned our universe upside down. It completely changed the way we see space and time, and it all starts with one simple idea that even you can understand. When Einstein was a young man, he worked at a patent office. He spent his days reading about and writing about inventions. But at night he thought about something else, the universe. He wondered what it would be like if he could chase a beam of light. Let's imagine that you are a race car driver. You're driving at 60 miles per hour. That means that every second you go 60 miles. If you want to double your speed, you have to double your effort. If you want to go 3 times faster, you need 3 times the power. But it doesn't work like that for light. Light always travels at the same speed, no matter how fast you move. No matter how hard you try, you can never catch up to it or outrun it. It always stays just out of reach. To make sense of this, Einstein did something crazy. He imagined that time itself changes depending on how fast you're moving. If you're standing still, time passes normally. But if you're chasing light at 60% of the speed of light, time slows down. For you, only 60% of each second passes. The other 40% is saved for when you catch up to the light. In other words, from the perspective of someone standing still, you would seem to be moving in slow motion. In 1905, Einstein published these ideas in a paper called "Does the Inertia of a Body Depend Upon Its Energy Content?" In it, he explained that mass and energy are interchangeable, and that the equivalence leads to an important consequence. The mass of a body increases with its energy content. So if you were to chase light and get closer and closer to the speed of light, you would also get heavier and heavier. The more energy you use to propel yourself, the more energy you have stored in your body, and the more energy you have stored in your body, the more massive you become. But the craziest part is that time really does slow down for objects that are moving really fast. It's called time dilation. It happens because space and time intertwined in a 4-dimensional fabric called spacetime are relative. They depend on how fast you're moving. When you're standing still, time passes normally. But when you start to move, time slows down. And the faster you move, the slower time goes. This is why clocks on fast-moving objects like satellites actually run slower than clocks on Earth. It's mind-bending to think about. But there's even more. Einstein also developed a theory of general relativity. It says that gravity isn't a force at all, but a curvature in space-time caused by mass. Imagine a bowling ball on a trampoline. It makes a small dip in the fabric. Now imagine a marble rolling around the trampoline. The marble doesn't feel anything. It just rolls around normally. But if it gets too close to the bowling ball, it will start to roll towards it. That's because the bowling ball warps the fabric of space-time. The marble can't see the warp, but it can feel it. It's the same thing with gravity. Massive objects like planets and stars warp space-time around them. And smaller objects like satellites and spaceships move through that warp. That's what causes gravity. Now, let's get back to our race car driver. He's chasing light at 60% of the speed of light. Remember, his clock is running slow. But now, let's imagine that he turns on the afterburners and accelerates to 80% of the speed of light. His clock will slow down even more. But here's the thing, everything else in the universe seems to be moving faster. That's because the laws of physics are the same for everyone. If he were to turn on his headlights and see another car in front of him, it would appear to be moving faster than the speed of light. It sounds impossible, but it's true. That's because the fabric of space-time is relative. It depends on how fast you're moving. When you're chasing light, the universe itself seems to be standing still. So remember, when you're in a race against light, you're not just racing through space. You're racing through time as well. And the faster you go, the slower time becomes. It's a weird and wonderful universe we live in. Let's explore some of the most mind-blowing aspects of Einstein's theories of special and general relativity. First off, you might have heard that time travel is theoretically possible according to relativity. But how does that work? Well, it all has to do with the fourth dimension. In addition to length, width, and height, our universe has a fourth dimension: time. These four dimensions are intertwined in a four-dimensional fabric called space-time. Now here's where things get weird. According to Einstein's theory of special relativity, time is relative. It depends on how fast you're moving. This means that time can pass differently for two observers who are moving relative to each other. Imagine you have a friend who decides to take a trip on a spaceship that's traveling close to the speed of light. While your friend is on the spaceship, time will pass normally for them. However, for you on Earth, time will pass much more slowly for your friend. This means that if your friend were to return to Earth after traveling close to the speed of light for a while, they would find that much less time has passed for them than for everyone else. They would effectively have traveled back in time. So technically, time travel is possible according to relativity. However, it's not possible for us to travel back in time in any meaningful way. We'd have to travel incredibly fast, close to the speed of light, which is currently beyond our technological capabilities. Additionally, even if we could travel close to the speed of light, the effects of time dilation would be so minuscule that it wouldn't be noticeable for everyday purposes. So, while time travel is theoretically possible, it's not something that we need to worry about anytime soon. Another mind-bending aspect of relativity is the equivalence principle. This is the idea that the effects of gravity are indistinguishable from the effects of acceleration. To understand this, imagine you're in a closed box on Earth. You weigh yourself and find that you weigh 100 pounds. Then you turn on the box's engine and accelerate upwards at 9.8 meters per second squared, which is the acceleration due to gravity on Earth. You turn off the engine and weigh yourself again. You'll still weigh 100 pounds. From your perspective, there's no way to tell whether you're accelerating upwards or sitting still on Earth. This is the equivalence principle. Gravity and acceleration are equivalent. Einstein realized that this equivalence principle could be used to develop a theory of gravity. His theory of general relativity, according to general relativity, massive objects warp the fabric of spacetime around them. This warping causes other objects to move towards them. This is what we experience as gravity. So technically, we're not attracted to other objects. Instead, we're simply following the curvature of spacetime. Finally, let's talk about the speed of light. As we mentioned earlier, the speed of light is the fastest speed at which anything can travel in the universe. It's approximately 299,792,458 meters per second. Nothing can travel faster than light because it's impossible. As an object approaches the speed of light, its mass increases infinitely, meaning that it would require an infinite amount of energy to accelerate it to the speed of light. But there's another reason why we can't travel faster than light. It has to do with the nature of spacetime itself. According to Einstein's theories, space and time are intertwined in a four-dimensional fabric. The speed of light is the fastest speed at which information can travel through this fabric. This is because the speed of light is the fundamental constant of nature. All other constants, including the gravitational constant and the mass of an electron, are derived from the speed of light. It's also worth noting that the speed of light is constant. It doesn't change over time or in different locations. This means that no matter where you are in the universe, you can always measure the speed of light to be approximately 299,792,458 meters per second. Overall, Einstein's theories of relativity have revolutionized our understanding of the universe. They've taught us that time is relative, that gravity is a curvature in spacetime, and that the speed of light is the fastest speed at which anything can travel. While these theories may seem strange and counterintuitive, they've been proven correct time and time again. They're the foundation of modern physics and have led to countless scientific discoveries and technological advancements. And if you want to learn more about Einstein's theories of relativity, check out the additional resources we have linked below. Thanks for watching, and we'll see you next time.